The meeting is finished. We usually adjourn to Abe and Herb in the Tannery building for drinks and food. Anybody who's interested, we'll usually do a show of hands to see who's headed over. So if you'd like to come and you don't know where you're going, find someone who's got a hand up and follow them. It's the same building where Desire to Learn is, where Google used to be, so it should be easy to find. All right, now we'll get off the stage. So, moving on to Haskell.
Okay, so the second half of the talk is on Haskell. You've seen lots of it already, but this goes into some more details of Haskell. So, what is Haskell's sort of approach to programming? Well, one thing I can say from my experience in learning and programming is it's very constrained. There's a lot of common bugs that happen in imperative programming that you simply can't do in Haskell. There's lots of different kinds of bugs that you can't do in Haskell because you're somewhat limited in what you can in what you can't do. But there's a lot of flexibility that the language has in what you can do. And so here this is only the Haskell way. I was talking to a friend of mine who programmed in Scala for a long time. And he said that in Scala there's all sorts of different ways to do it. There's the object-oriented way, there's the not object-oriented way, there's mutable data or immutable data. You can use for loops or you can use recursion and map and stuff like that. And so there's all sorts of different ways that you can solve things in Scala. But in Haskell, there's only the Haskell way. There's no loops, there's no mutability. That should have an asterisk because you can mutate stuff, but there's a sort of caveat to that. Anyways, so in Haskell, there's more one sort of clear channel that you have to go through to solve a problem. Haskell is what I would classify as a top-down. It makes lots of use of abstractions, lots of lambda calculus stuff, and category theory stuff. For some of the more complicated type things, having sort of rudimentary understanding of category theory is helpful. It's very safe. It's both safe from the point of view of making it difficult to make mistakes or certain classes of bugs, difficult to make mistakes where you have variables that are shared by other things that are changing because you just can't do that. And safe from the point of view of type safety. It's a very strongly typed language. You can't, there's no what's called type coercion. You can't coerce a integer into a long or a long back into an integer without explicitly converting it. It's very fast. It's compiled down to an executable file and is only a few times slower than C at a program if you program it in an idiomatic Haskell way. That's just using what's it called, the computer language showdown from Debian's Alioth machine, and it's also powerful. It lets you do lots of really cool stuff. So it's influenced by a lot of different languages. The red ones are the ones that we've seen, the main ones: FP, Lisp, ML, Standard ML, and Scheme. There's a whole bunch of other ones that I didn't even look into because there are so many of them. But it was a unification language designed by committee. So there are all sorts of different interesting ideas floating around in the sort of advanced functional programming world. And somebody said, okay, we need to kind of condense all these different ideas down into one language that will let us continue on and investigate all these really neat things using a sort of powerful language. And so it was designed by committee, but it's an example of something really good that has come out of something being done by a committee. And so what are the language features? It makes heavy use of curring, that's partial function application. It makes use of infix operators. Infix operators are like A plus B, where plus is the infix operator. And what that allows you to do, instead of having functions that always take things, that always appear on the left side of the variables, you're able to mix functions in with your variables, and it ends up being sort of more readable, left to right type of readability. It's concise. You can say a lot with a little in Haskell. The corollary of that is that it takes a long time sometimes to read through a function because you have to read carefully and understand everything that's going on. It makes use of pattern matching both in variable assignment and then function definition, which is really, really great. If you've never experienced pattern matching, you should look up the language that has it and just give it a try, or at least read about it, because it's really cool. Implicit functions, you can define functions implicitly. That's not really a big feature, but it's kind of cool that you can do it. And lazy evaluation, that's a big part of Haskell. So why program in Haskell specifically? It enforces safety. It's a strongly typed language. You can't make type errors at all. That helps it in terms of modularity. Functional programming is great at modularity, and having a typed language makes it even better because you can have all these sort of different blocks that you can stick together, and you're guaranteed that they fit together properly and the data is being passed together correctly. Enforce safety single assignment. You can't assign a variable and then, a question.
Sorry, can you say that again?
Like we have an integer that's 16 bits or 32 bits, 64 bits. How does that work across machines?
You have int that is platforming, and then you have integer which is unbounded. Those are the basic things.
So you see the integer to this that.
Well, as I said, there's no just like this, do some sort of serial.
That's for the text
Did he answer your question? Okay.
Right. Single assignment, you can assign a variable once, but you can't reassign it. So you can't say x equals 2 and then later on say x equals 3, because you're just not allowed to do that. So this is pure/contained IO. Haskell, another question.
So what you just said, you can only assign to a single variable. What about like a global variable? Would you assign it to inside it?
Okay, so the question is, can you assign something to a variable, or can you assign to a global variable? What was that your question? Sorry.
So you said you can only assign a single variable within the Haskell programming, correct?
Oh, you can only assign a variable once. So if you have a function that you're evaluating has some different things in it, you can say like y equals 3 or x equals 4, but you can't later on, once you've assigned a variable, reassign it to something else.
So you can't do it externally.
No, so a global variable, if you had two functions and they use some other sort of global variable called, I don't know, something else, you would be able to reference that global variable, but you wouldn't be able to change the variable, because that would be mutation, and you're not allowed to do that. But it is possible, which I will get to in the later monad stuff, because it is possible to have globally mutable variables in Haskell, but the way that you interact with them is in a sort of contained input-output context. So functions can be pure, which means that they don't have any side effects, and you can also have this is contained I/O. Whenever you have I/O, whenever you're causing a side effect, changing a global variable, or altering something that is outside of the context of your function, whether it be reading in from a disk or putting string out to the console, that happens in what's called the I/O monad, and your side effects are stuck inside that monad. They can't get out. So if you have a function that's not inside the I/O monad, it means that you don't have any side effects. You can't have any side effects. So smart shared state. You can have mutable variables. There are atomically mutable variables, and there's also software transactional memory that let you have multiple functions or multiple threads of execution communicating with each other through these global variables. But it's done in a way that is safe, instead of just having a global variable that any one of your functions can stomp on it at any point in time. And expressions, everything is an expression. This means that you can't have a forgotten return statement if you've got some if statements and you forget to return from one of them, and your function just kind of falls off. In Python, it would just return none in that case if you forget to return something. But in Haskell, everything is an expression, and everything returns returns something. Separation, why would you want to program in Haskell? Separating things into pure functions allows you to have fast function evaluation. The compiler is able to reorder functions or fuse them together based on efficiency, and because if there's no data shared between them, you don't have to worry about executing them out of order. If executing them in different order doesn't change the answer. Parallelism, you can evaluate pure functions in parallel using what are called sparks. And it's very easy to add parallelism into a functional program. You've got a map operation that's mapping function over a whole bunch of data. You just change that from map into parmap, and then there's a function that lets you evaluate something that's in the parmonad to convert it into your regular list. There's also concurrency. Haskell has sort of its own kind of threading. It's able to make use of operating system threads, but you can have a single-threaded Haskell program that has individual, separate Haskell threads inside it. And Haskell threads are very lightweight, allowing you to spawn tens or hundreds of thousands of threads without any real sort of operating system impact. And those threads can be communicating together and working together. If you do have a multi-core computer, you can compile your program with the threaded flag that lets those threads then execute on multiple cores. And modularity and reuse is another great reason. Because it's a statically typed language, you're able to guarantee that the little modular bits that you combine together, you don't have type errors, you're not forgetting that, you're not mixing up the things that you're returning from one function and putting into another function. And because it's functional, it allows you to break your problems down into small modular pieces that you can then stick together. And so another reason why programming in Haskell, lazy evaluation is another good reason. It lets you operate on infinite data structures. You can have infinite lists that you sort of work with. If you had a list of some finite length and you wanted to enumerate each one of those, one way of doing that is like I think there's a function in Python that lets you just take a list and zip it together with a list going from 1 up until the number of items in your list, and you end up with a tuple that has, the first item in the tuple is the number of your item in the list, and the second item in your tuple is just the item in your list. To do that in Haskell, you don't have to know what the length of your finite list is. You just zip your finite list with an infinite list going from 1 up to infinity, and zip knows to stop when it gets to the end of the shorter list. And so it just zips your infinite list together with your finite list, and then when your finite list ends, then it stops. So it lets you work with infinite lists. You can have infinite trees that you work with. You, of course, can't do an infinite amount of data processing with it. You can just work with these infinite structures in a way that doesn't require evaluating the entire thing, because Haskell's lazy. It won't evaluate it until you need it. And if you need it, then, well, it just takes more and more of the infinite data that you want. It's also efficient because it doesn't do anything that it doesn't have to do. If you want to take the length of a list that has been passed through a map, and you've got a really expensive function that you're mapping it with, if you just want to know the length, you don't have to evaluate the expensive function in the map. You're able to take the length of your list very quickly, because it doesn't actually have to evaluate the expensive function just to find out the length. And also, it's good for composition and modularity. If you've got a library that you're pulling some function from, and say you're composing that with one of your own functions, the function in the library could do a lot of expensive stuff depending on the type of data being passed in, but if it doesn't have to do that, then it doesn't do it. It only does what it needs to do to get to the answer that you want. One of the problems, though, this is not a feature, one of the problems is that it's hard to reason about. It's hard to do time benchmarking, and it's hard to do space benchmarking in the way that you might in a imperative language. In Python or C, if I want to know how long it takes to execute a function, I just measure what time it is before executing the function, call the function, measure what time it is after that. But in Haskell, you can't do that because of lazy evaluation. If you measure the time, and then you do an expensive function, and then measure the time, and then later print out the time, Haskell doesn't actually evaluate the time until you print it out, because it doesn't need that. When you try printing it out, it says, okay, I need the string representation of these two time things. Well, then it measures your two time things, which happen right after one another, and then convert it into a string and print it out, which gives you no time at all because the measurement of your time is separate from actually evaluating your function. But there are profiler options in the compiler. The main Haskell compiler is called GHC. It's a Glasgow Haskell compiler. And it has lots of profiling options that let you measure how much space your things are taking up, how much time your things are taking up. It's kind of like the Gymnastics compiler profiler. It gives you a sort of output of all the different functions and how much time they're taking up, how much memory they're taking up. And so in the tutorials on how do I profile things, or how do I figure out what's taking a long time in Haskell, the tutorials say, don't try to do it manually, just turn on the compiler options, read the output, and that will tell you what you want, because it's very hard to figure out what is actually happening with lazy evaluation. And so here are some other reasons why program in Haskell. It's very concise. It has a good foreign function interface. It lets you interface with C. It also has, there are some new libraries that are being developed that allow you to use different languages in line with Haskell. Haskell has the ability to do what's called template Haskell, which lets you use just some non-Haskell code that's contained in a block. And then it takes that and then puts it through a special interpreter that then does Haskell stuff behind the scenes with it. So you can program inline Python, and it will take your Python code, put that into a file, which then puts a C wrapper around it, which then links that into Haskell using C, and just allows you to call it very naturally in line. You can do it with Python, Java, C, or the statistical language R. It has lots of abstract power. It lets you do crazy things that you don't even think you can do with programming languages. This comes out of the academic stuff and the language research stuff, because it's really good at doing this kind of thing. And it has some advanced features which I'll get to toward the end. So functional purity. This is purity. It's safe. Pure functions have what's called referential transparency, which means that the outputs from your function only have to do with what is going into your function. This is in a pure function. If you call a pure function with the same inputs more than one time, it will give you the same output more than one time. Contrast this to a imperative language where you might pass a class into the function. Say the function prints out what variable x is in your class, but also increments variable x. Then you call it again, passing in the same class. Well, now the class has some internal state that's been changed. And as you call your function again and again, it increments your variable x, and you get different answers coming out of your function. In this case, it's a string that's being printed, but you could also return something having to do with the internal state there. And so, pure functions have referential transparency, which makes it easy to reason about it. The main nice thing about pure functions is that it's easy to reason about it. All the stuff that's happening has to do with the variables that you pass in. There's nothing funny going on, and because you're not allowed to change variables once they're passed in, there's nothing funny going on outside of your sort of mental context. And so it's easy to reason about what your functions are doing. And it's also really easy to compose functions together. You can have functions that are good at doing one thing. Because they don't depend on other stuff outside of themselves, you can compose them together, and they only do what you think they're going to do. And so in the end, the composition of all of them does what you think it's going to do. And this leads to safer programming. The type system in Haskell is very strict, which is a bit hard to get used to. In C, I'm used to just taking an int and using that in place of a long, because the compiler automatically transforms that into a long. But in Haskell, you don't do that. It will complain because you haven't explicitly specified that you want to convert it into a long. And it's hard to get used to because it's kind of annoying if you're not used to your compiler being so picky about it. But it's good because you can't make typecasting mistakes. The type system makes heavy use of polymorphism. This is different from the sense of object-oriented polymorphism. In object-oriented polymorphism, you are able to pass different classes into a function, and it's able to handle different types of classes based on the inheritance of those classes. Or in Java, if you're classes implement a certain interface, you can pass in different kinds of objects that implement those interfaces because the behavior is the same. But in Haskell, the type polymorphism allows you to make functions that work with different types. And you can have different input types, but also different output types. And so the functionality of your function changes based on the type that you're passing in or the type that you're trying to get out of it, or sometimes both. So one of a good example of a polymorphic function in Haskell is the read function. Read takes in a string and then outputs a variable of whatever type you want that is able to be read from the string. So in the example where I split the list up into chunks and I took the 1, 2, 3, all the numbers that were in strings and converted those to doubles. That function is a polymorphic function that takes in the string and knows that I'm converting it to a double and then converts it to a double. You can't do that for everything. You have to do it for something that implements what's called the read type class. And Haskell has type inference, which is called the Hindley-Milner type inference, and a few languages have this. And it makes it so you don't have to specify the types of your variables as you're going along, because it's able to figure out what the types are and kind of stitch it all together. And in Haskell, your functions, when you define a function, you have the types of variables going in, the types of variables coming out, and it helps the type system figure out all these sort of internal bits of what's going on. Sometimes, in a few cases, you'll have to explicitly, inside your functions, specify what you want the type of something to be, but that's rare. Mental gymnastics. Sometimes when you do fancy things, your types can get kind of complicated and can be difficult to sort of understand. Not difficult to understand what's going on, but there's a lot of little bits you kind of have to pick out to understand what's actually going on. It has algebraic data types, which I'll get to later, and makes use of type classes. Type classes are different than object-oriented classes. What type classes are is that they allow you to group data types under classes of functionality, what you're able to do with the data type. The read type class is something where you're able to take a data type and read it from a string, or the show class allows you to take a data type and turn it into a string. There's the num type class, which is for numbers like integers or floats or bellows. You can add and subtract them. There's the rational type class, which allows you to divide numbers. You can't do that with integers, but you can do it with rational types. Algebraic data types, here we go. This is a little technical, I guess, but algebraic data types, it's not something that I've really encountered in imperative programming. In imperative programming, I'm used to having structs or classes or interfloats, but what algebraic data types allow you to do is to have data types that have the same type. This is a Haskell definition for what's called the maybe type. So we have maybe A. And what this A here, this A is a placeholder that allows me to specify some other type here. It could be a maybe integer or a maybe double. And what this allows me to do is create a new type that sort of bundles my other type into a new type. And there's different ways that I can create a value of type maybe A. I can use what's called just A, which when you just specify just a variable, if your variable is an integer, for example, and you say just 1, then you have created a data type of maybe integer that is just 1. Or you can say that it's nothing. And what this allows you to do is have a data type that you can pass from your functions that can encode the possibility of failure. So in C, if you were to do this, you might pass a pointer. And if your pointer comes out as 0, then you know that something's gone wrong inside. But if it comes out as non-zero, then you dereference that pointer and it gives you the value. Or in Python, you might return none from your function if there's a failure, or return something else if it succeeds. But in Haskell, what you would return is maybe integer from your function. And if nothing comes out, that means that there was something wrong. But if just 1 comes out, that means it was successful, and the value of 1 has come out of my function. The data type either allows you to do the same thing, but allows you to, instead of returning nothing, it returns something different out. So it takes 2 types. Say I had an either string and integer. And what this allows me to do is instead of returning nothing in the case of a failure, I could return a left and then a string of what actually happened. Left value is too large or something like that. And if I return a right, number 1 comes out, and that would be that it succeeded and 1 is my answer. Or I could return, instead of an integer as my type B, I could return something more complicated. And the left would contain the string that explains what's going on if I were trying to parse something. I wanted to parse that into a complicated data structure. The left, if there's an error, might be a sort of human-readable explanation of what's wrong. And the right would contain my data structure when it's successfully parsed. There's some other stuff that I'll just skip over that, I should say. Yeah, and these types of algebraic data types can be emulated in C using what's called structured unions, and you can actually do it in the Haskell as well. The Haskell type system, types say a lot. You can figure out a lot of what a function is doing just by looking at the type of it. So Haskell types are specified using these two colons, and you would have seen this earlier in the example that I did in the first section if the font were legible. But let's say we have some function 1. We don't know what it does, but it takes in a string and returns an integer. What type of functions could take in a string and return an integer? Does anyone have any suggestions? Just shout it out.
Word count.
Word count, exactly. How about function 2? It takes here this arrow here. This is a type class constraint. So we know that our type A has to be a member of the num type class. So it takes in an A, and then another A, and then returns an A. And we know that A is a member of the number type class. So what type of function would take 2 numbers in and then return a number? Plus, exactly. How about function 3? Function 3 just returns a double, so there are no inputs, but it's just a double. And now remember, because this function is pure, it will always return the same thing because there are no inputs. So that means that function 3 is just a constant. It will return the same thing every time because it can't do anything differently because there are no inputs to the function. For function 4, here we see this IO. This IO is a data type, kind of like maybe or either, that lets you wrap another variable in it to create a new data type. But IO indicates the presence of a side effect. So there's some input-output going on here. So function 4 might be a random number generator where it consults the computer's random number generator to return a different value every time. Function 5, well, it takes a file path. This is a conveniently named data type and returns an IO string, so there's a side effect going on. What could function 5 do?
File read.
File read, exactly. And here's function 6. It takes a string and then returns an IO, but here this is called empty. There's nothing useful that comes out of this function, but it takes a string and does some kind of IO with it. What kind of function could that be? Print, exactly. Print to a screen.
What's function 3 again?
Function 3 is just a constant because it has, yes, question.
What's the difference between int and num?
Int and num, okay. Well, num is a type class, and what a type class does is it means that the members of the type class have to obey certain properties. So I can tell you exactly what num means if I broke the comp here. Let me tell you exactly what it means.
Int and double are instances of num.
Exactly.
So num would say like must have an addition property, must have a greater or less than. Yeah. It's just sort of by characteristics, not by actual content.
Yeah. So here let's just say maybe you can't see that, but anyways. Here. Let me make the font bigger. Here we go.
Oh yeah.
All right. Okay. So info num, class num, where it has to obey the addition, the subtraction, the multiplication, have a negate function, an absolute function, the signum, which just tells you whether it's as a plus or a negative sign, and it also has to be from integer, so it converts an integer into whatever type happens to be a member of this num class.
You have difference between int 32 and 64?
Sorry, can you say that again?
There is a difference between int32 and 64 in Haskell?
Yeah. So the normal integer data type, it has a certain number of bits that are, or a certain maximum value that's specified by the Haskell specification. But there's also a package called data.int that contains the int64, the int32, where you can explicitly specify what you want the length of your integer to be.
How about silent overflow? Haskell takes care of it?
About what?
Silent overflow.
Overflowing your variables is something that Haskell does not take care of. You can overflow a variable, I think, without Haskell detecting it. But Haskell does have the integer data type, which is arbitrary precision integer, which has no bounds to it. I don't know if Haskell throws an exception or not, if you overflow. I don't know. I've never tried it. Okay, so one thing you can do with if you take algebraic data types and type classes and combine them together. Yes, question?
Can you just go back to the function? Why did I get the last one? Thank you. Okay.
Okay. I think Paul is going to put these slides on the KWLog website, so you'll be able to access all these items. And so algebraic data types plus type classes equals contexts. And what these contexts allow you to do is to wrap data up into different contexts and do things differently based on what that context is. And so you can create these crazy things from category theory called monoids and functors, applicative functors and monads. Monoids are just things that can be concatenated together. Functors, I think we actually get into that in a second. I won't explain it now because we're going to get into it, because we have time. So monads provide isolation. What they allow you to do is to create these contexts that are kind of isolated, where things can happen in the context but can't get out of the context. And that's one of the great things about Haskell doing I/O in the I/O monad, is that your side effects are stuck inside the I/O monad and can't get out. So they're not able to leak into pure functions or anything like that. And it allows you to sort of have a better way of conceptually reasoning about where side effects are occurring and how they're being contained. And so, yeah, containment. Context-sensitive monads allow you to have different behavior based on the kind of monad that you're using. So we'll get into that as well. And it provides imperative-like syntactic sugar. Simon Peyton-Jones, who's the sort of main person behind developing the Haskell language, says Haskell is the finest imperative programming language, which I don't think that's necessarily true, but it's fun. And so this is kind of getting into some technical stuff. I don't know if people actually want me to go into this kind of detail, but I'll just kind of go over it. We saw with the num type class that things that are in the num type class have to obey certain functions. And so while we see the monad class, the thing inside the monad has to be a member of the applicative. Well, things that are in the applicative class has to be a member of functors. And functors, what does that mean? Well, functors have to implement a function called fmap. And so here's our data type A and our data type B that are wrapped inside this functor f. And what the fmap function does is it takes a function that goes from a type A to B, say it converts a string into an integer. And it's able to operate on your data inside your functor and then take that data and put it back inside the functor. It's pretty trivial thing, but that's what the fmap function does. Applicative functors, well, they're pretty much the same thing, because anything that's applicative also has to be a functor. And what it does, it has a function called peer that lets you take some data and then just encapsulate that in your functor f. It also has to have this other thing, which takes a function that maps A onto B, but your function this time, instead of just sitting out by itself, your function is encapsulated inside your functor, and is applied in exactly the same way to your data that's inside. So it just depends on where the function is, whether it's outside of your sort of functor context or inside. And monads have to do these other things too, but they now have this extra function here called bind. And bind is the main sort of monad function that takes a data type A that's wrapped inside your monad, and a function that operates not on your data in the monad, but it takes your data when it's outside of the monad, and then outputs a new type, but wrapped inside the monad. And then it takes this and then outputs the data that's wrapped inside the monad. So say you've got a string contained inside the monad. You read in from your console a number that the user types in. So that gives you a IO string. And then you do something that takes your string and say the read function. You want to convert that into an integer. And so you use the function called read maybe that takes your string and outputs that into oh no, this wouldn't work. Outputs that into, it takes a string and outputs that into, this is not a good example, I'm sorry. Anyways, so this part here, where you take in your data, you do some computation on it, but it's wrapped inside the monad, allows you to make the output of your thing context sensitive. And so this is where the context sensitivity comes in, where you can chain a bunch of these things together and it becomes context sensitive. I'll show you in just a second. Here's an example. I'll get to an example in a second. So different kinds of monads that we have the IM monad, which contains side effects. The STM monad, that's the software transactional memory. If you don't know what software transactional memory is, it's a really cool way of doing concurrent accessing on shared variables. Usually with like POSIX threads or with Python threading or something like that. You would have variables that you then sort of wrap in locks. So you would have a mutex and you acquire the lock, you read or change the variable, and then you release the lock. If you have a bunch of threads doing that, you can end up with deadlock or race conditions or all the other types of junk that happen when you're doing concurrent programming. But what STM allows you to do, you can define these variables that are software transaction memory variables, and you can just sort of like freeform operate on these things, and then execute that all in what's called a atomic block. So it does all of those, it tries to do all of those things. If you have multiple threads trying to do the same things at the same time, or they're doing different things, but they make use of the same variable. If you have multiple threads trying to do the same thing at the same time, it's able to detect that, and one of those is allowed to succeed, and the other fails and tries again. So it's kind of like databases, where you can have many things updating the database at the same time, and the database is able to handle this all in a sort of atomic and consistent way. But this is applied to memory accessing, which allows you to do really crazy concurrent programming, because you don't have to think about locking and unlocking and race conditions or deadlocks or any of that kind of stuff. You just program as you normally would, but wrap that in an atomic block, and it's very efficient, very fast, very easy to reason about. The nice thing about it is that you can compose different software transaction memory blocks together, which you can't do in threaded programming, because if you have something, say a bank transaction, you're trying to read a variable from one bank account and then write it into another bank account. If you take a lock on a bank account, read a number in, and then release a lock, that's sort of one sort of chunk of functionality that gives you a number. The second chunk of functionality, say you want to try to compose these two chunks together. You take a lock on another bank account, then write the variable in there, and then release the lock. If you try composing those together, it doesn't work, because you need to lock both things at the same time, read from one and write to the other, and then unlock them both at the same time. So you can't split the functionality apart into a smaller piece. With software transaction memory, you can, because there's smaller bits that you compose together, then get executed all within the one big atomic context. The ST monad also allows you to do imperative-like programming within sort of isolated context. So you can do loops, you can do globally mutable variables, you can do multiple assignment and all that type of stuff inside the ST monad, but that's all encapsulated, and you can't have one ST context talk to another. So that allows you to do safe imperative programming. But it's not as efficient as real imperative programming. You wouldn't want to try doing something that you would do in C inside the ST monad, because it's much slower than if you were to do it idiomatically in Haskell. There are a bunch of other types. One of the most interesting types is the state monad, that allows you to have what appears to be globally mutable state from the standpoint of the functions that make use of it, but it's not. It's just using the same state that gets passed on from one application of the function to the other. And so it appears as though you have readable and writable global variables but you don't really. You can't access them concurrently, and it's all done in a safe way that is without mutation, because your state is a thing that gets sort of passed on from one function invocation to the other, and it just ends up being implicit, some sort of implicit thing that isn't explicitly passing your functions, but is available for reading and writing. And so here's an example of the maybe monad. So here's just a reminder of what different functions monads have to implement. So we say instance monad maybe, which means we're defining maybe as an instance of a monad type class. And return x, return just takes some variable and then bundles that into your monad. Well, that's just easy. Return x is just x. So that's the simplest way that you can encapsulate a piece of information, wrap it into your data type maybe. And the bind function here, there are two different ways that we can operate on bind, because we can take, bind takes some data A inside your monad, and then a function that converts your A into, and outputs into your, a new type B, still in your monad, and then just outputs that type B inside your monad. So if we start with our A as nothing, well, there's nothing inside to have your function operate on. So we're able to define this bind operation implicitly using pattern matching in the case where we're trying to pass nothing into it. Well, if you pass nothing in, it doesn't matter what your function is, nothing's going to come out of it because there's nothing in there. But if you do have something in it, if you have just x, and you try to apply f to it, well, that's just equal to fx. And so what this allows you to do, the bind operation allows you to operate, in this case, in the maybe monad, in the presence of a failure. So if you have a sort of stream of, or a list of operations that you're performing, if at any point one of those functions fails, then the next time you try to operate on the data that's coming out of that, it will give you nothing. There's still state of nothing. So you'll see in just one second how that actually works. So here's an example of how this actually works. So let's say we have a function called, how do we do this? Checkstring. What checkstring does is it takes in a string. Is everyone able to see this all right? This font's a bit bigger. Okay, so checkstring takes in a string and returns maybe a double. So this is the type definition here, and then this is how the function is actually defined. The check string, we pass it some input, and now we see this do. This is the monad syntactic sugar that lets us do a bunch of different steps in imperative-like fashion, but converts it into a really nested expression that uses the bind operator and passes data down this big long string of expressions. And so we use a function called readMaybe that takes our input string, and we try to read this into a double. But if that fails, then our value will end up being nothing. But if it succeeds, then it will end up being just our value, which is a double. And so we apply our inbounds function to it, and what inbounds does is it takes a double and returns maybe a double. So it takes our value, and if the value is less than 10, then it returns nothing, which means it's failed. But otherwise, it returns just our value. And so we then take our val1, which we maybe read in. If this succeeded, maybe it didn't succeed. But we're able to read this in and apply it to the inbounds function, and then we'll get a value 2 out, or maybe not. If it succeeds, then we will. We'll get a just with our number out of it. But if it doesn't succeed, then we'll get a nothing. And then we try returning 4 plus 5 times our value 2. And if it succeeded, if both of these succeeded, then we'll end up getting success here, and our function will return the double in maybe. But if it did succeed, then it will return nothing. So let's try this. Let's check string foo. Well, foo is not a number, so this thing fails here. And it doesn't have to evaluate these other things. It just returns nothing right away. If we check string 5, well, 5 can be converted to a double. That's great. We return just 5 here. But then we try evaluating our inbounds function, but it's less than 10, so it returns nothing. So it fails at this point here. It doesn't return this. It just returns nothing. But if we do check string 20, then it's able to be read into a double successfully. It's inbounds, and so this returns just 20. And then we evaluate this expression here, which then just gives us just 104. And so this is how we're able to have a function that's able to encode the possibility of failure occurring or success occurring. And so now let's get on to side effects. We're almost at the end of the talk. Side effects happen inside the IO monad, and they can't escape from the IO monad. So this means that anything you do that has a side effect is not able to get into a pure function, and your pure functions aren't able to make anything happen that causes a side effect. And when you're programming, what this makes you do is kind of push your side effects to the edges of your program. If you had to read in a file at the beginning, you would read in the file into a string, like I did with my example that did these sort of splitting things up. Then you do a bunch of operations on that using pure functions only, and then finally when you have your answer at the end, then you'd output that. You'd write it to a file, or you write it out to the console, or something like that. And yeah, so then you try to have a pure functional core. The pure functional core is easy to reason about. You don't have any funny stuff going on. There's no mutation going on. So you try to program in a way that gives you as large a chunk of pure code as possible. And so some more advanced stuff you can do with Haskell, applicative functors. We saw that in the applicative type class, but you can do command line parsing and other parsing things. Applicative functors are really good at parsing things. Category theory, that's a sort of mathematical topic that is not necessarily related to Haskell, although to be able to understand a lot of Haskell type stuff, it helps to have a little bit of an understanding of what's going on in category theory. Concurrency, you can do really cool stuff with atomic immutable variables or software transaction memory. I touched on that a bit. Parallelism, it's really easy to do stuff in parallel. Laziness is under the advanced topics because it's kind of hard to understand. Laziness also affects parallelism. Sometimes Haskell's laziness gets in the way of executing things in parallel because it only evaluates a small bit in parallel and then later defers the more meaty stuff for later when you're trying to add up a bunch of numbers, which it's kind of confusing. So that's one of the sort of problems with laziness. Monad transformers allow you to layer monads on top of each other, so you can combine, say, the maybe monad, which includes failure, with the state monad that allows you to pass state between your functions. Pipe and conduit allow you to do streaming data processing in a fixed amount of memory. I encountered a problem when I was reading in a 500 meg file with 1.2 million lines and turning that into database operations that I then put into a SQLite database. Because I was reading in a whole bunch of stuff and doing monad operations on it, the database inserts had side effects, so they're monadic operations. And those were causing memory bloat, and the program ended up taking a huge amount of memory. But I wrote it to use pipe and conduit, which are designed for doing streaming processing on large amounts of data, but in a small amount of memory. And I was able to get it so it didn't take up hardly any memory at all. Arrows allow you to do really crazy functional composition stuff. One of the problems with functional composition is that the output of one of your functions has to be the same type as the input of another function. So if you have a function that outputs something in a monad, but you have another function that isn't expecting their input to come in from a monad, but the types still match. You've got like maybe a double, then you've got a double. The types don't match. And so arrows allow you to get around that and allow you to do composition where your input and output types can be a lot more flexible than what you can do with regular function composition. The lens library allows you to operate on data structures in a general way to be able to reach in and read and mutate data structures. I say mutate because the output of one of your functions that mutates your data structure is just the mutated data structure. So it's not actually changing data structures, just returning a new data structure that is the sort of changed version of the original one. Parsers, Haskell's really great at doing parsers. There's all kinds of JSON parsers and I'm not too familiar with parsers, but no, there's a really good JSON one. Persistent is like an object relational mapper that allows you to operate with Haskell data types and transparently use those in in relational databases. Free monads are really weird and allow you to do kind of computations without without actually mutating, without actually incorporating, using any data. It allows you to do things using data types alone, and it just alters the types of the variables that are coming in and out of your functions without actually doing any calculations. It's kind of weird. Crazy type extensions. There are all sorts of weird things you can do with types. Because Haskell's typing is so strong, you can have heterogeneous lists, which instead of a list having all the same data type, you can have different data types. But the way you do that is by doing really complicated type stuff. Template Haskell allows you to define domain-specific languages, so you can write inline Python code, which then gets interpreted and put into a Python file, and a bunch of crazy things happen. You can have domain-specific languages for operating on your database with persistent here, or other things that allow you to do a lot of complicated Haskell stuff behind the scenes using a really simple sort of special domain-specific language. Made-up programming allows you to do programming with the types. That's kind of like what free monads do. And there's all kinds of other crazy stuff you can do. And so, in summary, functional programming with Haskell equals cool. It exposes you to new ideas. It helps to make you a better programmer, just like making you more well-rounded in the different techniques of programming that there are out there. It can help make you a safer programmer by being exposed to a language that forces you to do things safely. You can say, oh, maybe next time I'm writing in C, I'll do things a little bit differently. Because I realize that maybe doing things this way that I've done things in the past is not really the safest way to do it. It has amazing concurrency. Both Clojure and Haskell have incredible software transaction memory libraries, which allow you to do really efficient, really safe concurrency. It's really fast, kind of brain-bending. Some of the mental gymnastics you have to go through to understand some of the more complicated type stuff is brain-bending. Horizon expanding, counter new things, and it's challenging and fun. When I'm programming in imperative languages, I really miss a lot of the abilities that Haskell and even functional programming in general has. What's up? Does anyone have any questions? Yes?
If you can go back to the monad example, applicative is a keyword there of the language?
Here?
Yeah. The first class.
So applicative is a class. But this is the arrow here, which means that your M in your monad has to be an instance of the applicative type class. And so the applicative type class is here. Whatever your applicative variable is, it has to be a class of functor, but in order to be a member of the applicative class, it has to implement pure and this star operation here.
And the class is the keyword of the language? Class?
Yes.
Oh, okay.
Yeah, so class defines a type class, like class num, or class read, or class show, class monad, class, so class applicable. Yeah.
And another question, you mentioned that you were using some stuff at work.
Yeah.
So what kind of application, how big they are, or?
Well, it's just very small. Usually what I use it for is parsing through logs and doing some complicated stuff with that. I mostly use that just to get experience programming Haskell, doing more challenging problems. I could do it in Python, but it wouldn't give me the exposure to Haskell. The one thing that I am using Haskell for, though, is there's a web framework called Yizod that is a web framework that lets you incorporate database stuff into just a general web application. It's kind of like Django or something like that, but it's in Haskell, and it's extremely fast. And I chose that over Python just because of Haskell's type safety and because of its speed, and also because it forces me to learn Haskell, which is what I want to do.
So how big of application can you build with Haskell?
You can build huge applications. Let me just think of how to answer that question. One of the sort of limitations that I experience with dynamic languages is because they're untyped, the sort of mental load that you incur as your program gets bigger and bigger. If you try refactoring something or taking a piece and you want to stick it into something else or change a piece, you kind of have to understand where where that function is being called everywhere and the kind of data that's coming out of it because your language is untyped. If you change something, then you don't have your compiler to say, oh, here and here and here and here and here and here and here need to be changed because your type is now wrong. You have to read through your entire program and or re-execute it, or if you have unit tests done and your unit tests fail and you know where you need to go, but because it's a typed language, this is the same as C# or C++ or Java. Because your language is typed, it allows you to make changes in your program and figure out exactly where that change is sort of needs to be altered elsewhere in your program on the type level. That doesn't help you if you change your +1 to a +2, and you shouldn't have done that. But so in terms of how big can your programs be, I mean, you can build really, really big programs with it. People in the finance industry use Haskell a lot because of its really strong type safety. If you're doing lots of number manipulation, you don't want to end up with any unexpected errors because of type errors or because you cast a long to an int and you tossed away the top 16 bits of information. Yeah, does that kind of answer your question? And also in terms of the size of your program, because functional programming languages, this isn't necessarily a feature of Haskell, but functional languages in general allow you to have more isolated and clean sort of blocks of your functions, so you can combine them together better, and your programs scale better because of how the language is put together. Yeah, two functions. Person in the blue. I'll get to you soon.
Does Haskell have a system library? So, for example, can you open network sockets?
So Haskell has lots of different libraries. There's a sort of library repository called Package, and there are at least, I think there's like several thousand packages in there right now. Haskell has core libraries that let you do certain things that are included in the language, but it has all kinds of other libraries. So there's the Yazod, which is the web framework. There's Persistent, which is the object relational mapper. There's parsers. There's web socket stuff. That's just a small list. And yeah, now did that answer your question?
Yeah.
Okay, and now, sorry, the person with the white and gray and yellow structure.
Yeah, what did you say you used instead of Python?
I used Haskell instead of Python.
Oh, you did? Okay.
Yeah, so I use Python a lot in my job as well, but I force myself to use Haskell sometimes for
every pointer type implicitly has the number null. And there's no, you can't do anything about that. So whenever you see some code you're not familiar with, you see a pointer, it might be null, you don't know. In Haskell, you would use maybe instead to explicitly state that there's, nothing is one of the possibilities. And you have to explicitly decompose that maybe to safely get the value of it without accidentally dereferencing it and blowing up.
Okay, so I'll just repeat that in case people didn't hear it. Okay, so another case where the type safety comes in really handy is in null pointers. You don't really have null pointers in Haskell, but in C++, one common way of returning a failure from a function is to return a pointer to your data, and if there's a failure, then your pointer ends up being null. You just set it equal to a 0. But if you try dereferencing that pointer, say you forgot that the pointer could possibly be 0. If you try dereferencing your null pointer, you'll end up with your software crashing. And it's hard to track down because you're still dereferencing a pointer, which at the type level you can do. And your pointer can also be null because it's just an integer to memory location. But in Haskell, instead of doing that, returning something which can be 0 or a null pointer, you just wrap your data in the maybe type, and if a failure happens, then nothing will come out of it. And if a failure doesn't happen, then you'll get just your data coming in. Any other? Did that answer your question? It was your question, yes. Any other questions? Okay.
They take the